Welcome, dynamic students, to our final lecture in our rigid body planar motion kinematics chapter. So for this last lecture, we're going to be tackling relative acceleration of two rigid bodies. And to do that, we're going to leverage and just literally build on what we did in our previous lecture, where we derived expressions for velocities in one reference frame relative to another reference frame, and especially using the key of this tagged reference frame motion versus another, where we look at the motion of one reference frame, maybe a moving one with reference to a fixed reference frame, via the motion of just one point of interest. And we called it point P in our derivation. So we're going to build on that and look at relative accelerations. And to do that, we are going to start with the expression that we already derived for velocity of a moving point in a, we'll call it a fixed reference frame F, and relating that to the velocity of that same point in a moving reference frame B, and then characteristics of the movement of that moving reference frame versus the fixed reference frame. So if you want to look back in your notes, a couple of pages, you'll find this expression. And just to review what the terms are, I already said v of p slash f means the velocity of point P with respect to the F reference frame. V of p and b is the velocity of P with respect to the B reference frame, which we're assuming is moving, generally speaking, plus the velocity of O prime, which is like the origin point of the B reference frame with respect to F. So this is effectively a way of saying the velocity of the whole B reference frame with respect to the F reference frame, times the cross product of the angular velocity of reference frame B with respect to reference frame F crossed into a radius vector from some known point in reference frame B, like its origin O prime to P, the point of interest. So we're going to take that whole expression and we're going to take the first derivative with respect to T so that we can get an acceleration of our point of interest P with respect to the fixed F reference frame. So we're just going to start taking time derivatives. And so I'm gonna just sort of draw lines from what was the velocity expression, and with the line we'll pretend we just took the derivative with respect to t. So we take the derivative of v velocity of P with respect to the F reference frame, and of course this gives us acceleration of P with respect to the F reference frame. If we take the velocity of P with respect to the B reference frame, and we take the time derivative with respect to the F reference frame, we get another one of these kind of mixed reference frame time derivatives. We got the time derivative as denoted by the dot, but we're talking about a velocity of P with respect to B, and now we're taking the time derivative of that with another different reference frame F. Well, we're back to that kind of miserable point that we were when we were looking at the time rate of change of the radius vector from the origin point in B to P with respect to the F reference frame. So we're just gonna use the same remedy that we did. We're going to apply this relationship that says, well, we can replace this kind of mixed reference frame time derivative with one that is all reference to the same reference frame, namely in this case the B. So we can replace this term with this expression that says, okay, we can replace this with the velocity, the first time derivative of the velocity of P with respect to the B reference frame with respect to B. So that's just acceleration of P in B. Great. Something that we could presumably measure if we're standing in B. Plus the angular velocity of reference frame B with respect to reference frame F, which we've already have up there, and then crossed into the velocity of P in B, which we already have. So all of these terms are good. We already know them, or we have ways of getting them. So moving on to the next term over here, we're going to take the time derivative of the velocity of O prime, which is kind of the origin of reference frame B with respect to reference frame A. So this is the kind of the translational velocity of reference frame B with respect to reference frame O. If we take a time derivative, we just get the translational acceleration of reference frame B, denoted by its origin point with respect to reference frame F. Cool. Now we're going to take the time derivative of a product. So we're going to end up getting, the time derivative of this first, still crossed into the second, plus this term, by itself, crossed into the time derivative of the second. So we'll start with the first of those. We're going to end up taking the time derivative of what's effectively omega k hat, and we're going to get alpha k hat. So this is the angular acceleration of reference frame B with respect to reference frame F. And that'll just be crossed into our radius vector from some known point in reference frame B to P, our point of interest. Then we've got, omega t crossed into one of these mixed time derivatives again. And this is a familiar one. We saw this when we were deriving our relative velocity expression. So we've just got the time derivative of the radius vector from the origin of reference frame B to P, or point of interest, with respect to F. So of course we're gonna do our switcheroo formula, which we derived in the previous lecture, and is analogous to what we applied over here, except this is literally what we did before because we're working with radius and velocity. So we can equate this term with the time rate of change of our O prime P within the beta reference frame with respect to the beta reference frame, which just becomes the velocity of P within B with respect to B, plus rotation rate, angular velocity of reference frame B with respect to reference frame F crossed into our O prime P. So now we get to do a whole lot of collecting of terms. So we're ending up with quite the long expression here, but each thing is fairly simple. So we're just literally taking everything on this line and rewriting it in a big line, and then showing that cross product being distributed over multiple terms. So again, what we were looking for is the acceleration of some point P with respect to, say, a fixed reference frame that we can measure from. So that'll be the acceleration of that same point with respect to our reference frame B, maybe a moving reference frame, plus the angular velocity of our reference frame B with respect to reference frame F crossed into velocity of that point within reference frame B, plus the translational acceleration of reference frame B with respect to reference frame F, so movement between the reference frames themselves, translational, plus the angular acceleration of reference frame B with respect to reference frame F crossed into the position of our point of interest P with respect to a known point in reference frame B, plus this long cross product where we've got our angular velocity being crossed into the sum of the velocity of P with respect to reference frame B, which is going to give us another one of these. And then we're going to end up with another one of those triple cross products where we've got angular velocity crossed into angular velocity crossed into our O prime P. So we're going to start by just looking at this product. We're going to end up with a second O prime cross velocity of P within reference frame B, and that'll add to this one, so we end up with two of these in our final expression. The other expressions we're just going to rewrite. They're pretty simple. There's one for wanting them here. And then we've got our triple cross product, which if we use our triple cross product vector algebra identity, we can end up getting a negative theta dot, otherwise as an omega or angular velocity of reference frame B with respect to reference frame F squared. That's angular velocity squared in the direction of, and that's just the it's the magnitude of the angular velocity, actually, not the vector. We've dropped off the k. The magnitude of the angular velocity of those two reference frames relative to one another, times the radius vector of O prime to point of interest P. So if we take a look at that, we're gonna rewrite again. We're doing a lot of rewriting and simplifying. So we've got basically full acceleration of P with respect to F equals acceleration of P with respect to its B reference frame plus this big long expression, which basically is a way of again expressing the acceleration of reference frame B with respect to reference frame F tagged to point P. So if we look at point P as the point at which we're evaluating all of this, that whole expression, this term, this cross product minus this scalar product, is going to equal the relative acceleration of B and F, B with respect to F, from the standpoint of point P. So P is our tag point that we're using to kind of show how B is moving, accelerating in this case with respect to F. Then we got this leftover term that fell out of our triple cross product, and that is proportional to angular velocities and the velocity of point P within the moving reference frame. And that is referred to as the Coriolis acceleration, and it is basically, it's going to be moving in a direction that's perpendicular to a lot of the other terms. And those of you who are interested in weather, you'll notice this term being used to express why certain things like ocean currents and prevailing wind patterns will rotate in certain places. This is the particular acceleration in the spherical coordinates of the Earth that is responsible for some of that. So now we've got a general expression that relates motion of a given point, its acceleration, in a moving reference frame B with respect to, we'll call it a fixed reference frame F, using terms that we can hopefully evaluate. So as an example application of that, I'm not going to flip back to the example because you can go back in your notes to it. We could apply the equation that we just derived to the same example that we worked in the previous lecture, where we had a sliding body going back and forth in a bearing race, being pushed by a rotating rod in a fixed reference frame, and looking for an expression for the velocity with respect to the fixed reference frame of the sliding block, and having to use our relative reference frame concepts to relate motion of the rod to motion of the block to the fixed reference frame. So I would refer you to that previous lecture if you want to go over that. But we can extend that and extrapolate what we did in that example to acceleration of that point Q on the block at the time that the rod angle, rotating rod, was at 60 degrees, assuming we knew something about the acceleration of the rod. Because in that particular problem, it was the rod that we would equate to reference frame B, the moving reference frame, and in this case it was only rotating with respect to the fixed reference frame. So we were given a rotation rate in the previous problem, and I believe it was 20 radians per second. It was going clockwise, so that was negative, a negative number given our default coordinate system for F, which was counterclockwise positive. And now we're denoting an alpha of 30 radians per second, so that's positive. So it's moving in the clockwise direction, but it's accelerating in the counterclockwise. So we can basically go one for one with the equation we just derived and do a bit of a plug and chug to see how point Q would be accelerating down the slot in the I hat direction, which was the only direction that we found it could go. So we can look at acceleration of q in its fixed reference frame as being the sum of q with respect to the rod reference frame, that acceleration, which we don't know the magnitude, but we know that it has to, just as was the case in velocity, with respect to the r reference frame, q's kind of going in a straight line up or down the rod. That's the only way that it can move, and it's the only way that it can accelerate. So we have a fixed direction for that, just as we did in the case of velocity. Now we're going down the terms acceleration of point O with respect to the fixed reference frame. We could say O prime, which would be utilizing the equation we just derived directly, which would be sort of the origin of our rod moving reference frame. Well, in this case, O prime and O are the same point. So that makes it even easier. So we can look at the acceleration of that origin, that axis of pivot point of rotation of the rod with respect to the fixed reference frame. Well, it's zero, because the pivot point is not moving with respect to like the hinge that it's pivoting within. So that turns out to be zero. We already have the radius from that pivot point, that point O to T that we calculated in the last example, and then of course our theta double prime is alpha, so we have a numerical value for that. We already have a numerical value for theta dot, so that was omega, that we can drop into this term, and likewise same here. And then our velocity of q with respect to r is what we already calculated in the previous problem. That was what we were looking for. So if we put all of those together and rewrite the expression for each one, we can just kind of tally up each of these vector expressions together, and then we're going to reassemble all of those as a sum. And I'm not showing all of the rearranging, but we can take each of these expressions that we then, I believe they're all just added according to this formula. We can collect the I hat terms and the j hat terms and solve for acceleration of q with respect to r. So q is accelerating, has a positive number, so it's actually accelerating in the negative I hat direction, so it's kind of going out the bar. So the velocity was towards the pivot point, the acceleration is away from the pivot point, probably because of that positive value of alpha on the rod. And then if we collect the I hat terms together, we get our value of the magnitude of acceleration of point Q with respect to the fixed reference frame, the bearing and the hinge and all of that. So it's sliding, it would have a negative acceleration down the race, or down the slider in the I hat direction. So with the exception of just pulling values that we already designated, key points again were looking at acceleration of q with respect to the rod r, and recognizing that it, like velocity, was going to be constrained to either up the rod or down the rod. Now remember, if you've got a curved system, velocity and acceleration are rarely in the same direction. So we basically had a 1D motion for Q and R, because Q could only slide up and down R, and so that direction of sliding would be based on the orientation of R in the fixed reference frame. And again, we're using I hat, j hat, which are the coordinates for F. So we're expressing everything in terms of the F reference frame unit vectors. So those are kind of the common currency, because we've converted everything. And everything else is drawn from our previous example. So we're just basically knowing what to plug in. Oh, and recognition that O prime, the origin of the moving reference frame R, and the origin O of our fixed reference frame happen to be the same. So O and O prime are the same. So we zeroed out a term. But with that exception, we're just literally we're leveraging our we're leveraging this expression using its more detailed form and things that we can find. So that concludes our rigid body planar kinematics section. It's probably the longest section or longest topical module in this particular dynamics course, and definitely the concepts of relative motion and relative reference frame motion, and then application of that to a real system is probably one of the more difficult concepts that we'll cover in this course. And so the key is to practice, to get used to seeing, okay, what am I going to designate as a fixed reference frame? What's the next one? And remember, each and every rigid body really has to be thought of as having its own reference frame. So there's relationships we use to look at velocity and acceleration of 2 points on the same reference frame if we know that or on the same rigid body if we know that rigid body's motion versus something else. And then we always make sure we have a unique reference frame to describe the motion of each body. And then if we're looking for body to body, we go to this section and start saying, okay, I've got one body, I got one reference frame. Who am I going to assume is standing still and use its unit vectors basically as a common currency, and then start applying these equations that we derive for velocity and acceleration for one body to another. So as the best suggestions, along with a lot of practice. And so we'll be jumping into Newton's and Euler's second law and taking all of these great expressions for acceleration and then using those laws to relate them to the sum of our applied forces and moments on the rigid bodies, and seeing how those relate to what we did with kinematics. We'll be utilizing a few new concepts like moment of inertia, products of inertia, and relating those to angular momentum in a little bit different manner than we saw for particle angular momentum. So if you have covered moment of inertia as part of your statics or your physics courses, now would be a great time to dust off those old notes and lectures and give a review of what moment of inertia is and how to calculate it, since we'll definitely be using that as a workhorse as we go into rigid body planar kinetics. So see you next time for that.